Okay, so I think we can start with the discussion. There will be few who will be joining late. Till now, we have discussed about QGIS software and different aspect of spatial data. So we are slowly moving toward building and playing with different types of data sets and also working on the different forms of the data set. Now, as most of you are working with the Python, so the most important data format that you will be getting is it would be a tabular form, and we know that pandas are used to handle our data set, which is more like tabular data. But if we talk about spatial data, that will be handled in via GeoPandas. So this is a library that has spatial functions, and those can be applied onto the data set which has a geometry feature. So in the previous lecture, we discussed about the tabular form, how to use the GeoPandas to create the geometry based data set. We call it a spatial data. So it has a geometry column along with it. So there are three geometries that we discussed: the point, the line, and then we have polygon. So these three geometries are there, which will be having a value in the geometry column of the data set. So it will be a normal data frame, but one of the column would be of geometry. So normally, if we go deeper into different softwares, it is normally called as geonorm. So whenever we will be working with QGIS, there you will see the default name for the geometry table is geonorm, and whereas in for GeoPandas, it is geometry. You can certainly give another name to the geometry, but this is a standard practice that whenever you have a geometry saved, that particular column would be called geometry in pandas. So we discussed that. We also worked on QGIS and created isochrones. I hope that you have worked on your part. I got one email from one of the student about the completion of the assignment. So it is good. And what I expect is you work on your side and you learn about all these aspects, because spatial data is going to be huge. That's for sure. And everyone is talking about this because the knowledge of where is very, very important. This all combines together the big data technologies, the decision making, machine learning, and location intelligence. So everyone is talking about location intelligence. So please work on the stuff that I'm sharing. Certainly, it is not that extensive where you can actually implement a project, but these are small use cases that you can build and use to further enhance your skill. So in today's class, we will be focusing on the rest of the notebooks and also move forward with the one of the chapter from the book, which we started to discuss. So first is the coordinate reference system. If you open this and walk along, that would be also wonderful. Coordinate reference system is very, very important for each and every spatial data. So we have discussed about this when we were discussing QGIS. I've shown you what the CRS system has been used. Normally, what happens is the spatial reference system is given in a particular number. We call that number as EPSG number. So I'm looking at where it has been given. Okay, so coordinate reference system is certainly, as we have discussed, it represents the longitude and latitude of the data set. So what we want is to actually showcase the coordinates over the earth onto a 2D plane. So whenever you will be working on the data set in pandas, it is considered that your data is actually converted into 2D plane. So actually it is elliptical, but it has to be converted into 2D plane. So when we say it has to be converted into a 2D plane, it has to have some CRS. So that CRS is coordinate reference system, by which this three-dimensional map is actually converted into two-dimensional map. So there are different types of projections that is not of much use for us, but certainly you can go deeper into this if you want to get more knowledge. You will find more mathematical terms, how you are basically converting a three-dimensional space to two-dimensional space. There are obviously, if we peel orange and try to put those the peeled cover on a flat surface, then you will see the deformation is always there. So certain formulas, certain coordinate system try to preserve the properties. Certain CRS system will try to preserve the shapes. So such are the system which tries to, accommodate and save as much as possible the data while converting from 3D to 2D. Now, a simplistic case for you guys is we have discussed about geo data frame, and when it is a geo data frame, it can be its geometry can be accessed by our this CRS method. So it will return you what CRS is being used. So here you can see for the country's data that we have uploaded on the top of this notebook. So country's data has a CRS of WSG84. Normally, when you transfer the data set, and universally accepted data format is WSG84, because in this, the latitude and longitude are given in degrees. And whenever we have to process the data set, we have to convert these degrees into the required units. So let us suppose your job is to process the distance between 2 points, then you have to convert this data set into a right kind of CRS system. So let us suppose if your CRS is WSG84, then the point distance between these 2 points A and B would be considered as an angle. So it will return it as an angle. But if you want that it has to be some the distance you want in meters, then you have to first convert this into a proper EPSG. It is European Petroleum Survey Group. They have given the number to each and every CRS system. So you normally need to remember this EPSG number. This we have discussed when we are discussing about QGIS. So if there are 2 points, let us suppose that I think if I'm not mistaken, so there is 642 32,642 is one EPSG, and in that the distance would be in meters. So when your CRS is converted into this, when your data is converted into this CRS, then the distance between A to B would be in meters. We will see all this stuff shortly, and let's move forward. Now, plot function is available as for the pandas. So it will actually plot, and it knows that which one is the geometry column. So it will try to plot the data from taking the geometry. So here you can see that this is countries data, and we can see the what values are there. So if you wanted to see the data set, okay, so I have to define, sorry. So here we can see this is a polygon, and multi-polygon is also there. So this is a different types of data set we would be having. Now, one single row is used to represent one attribute, one particular observation. And this geometry feature is used to represent what type of feature it is. So it's a polygon, and it would be plotted via plot function. Then within this CRS representation, there is dot proj string. This dot proj string is used to represent what is the projection system and what is the datum. Datum is a point where is used to start the starting point where x and y, lat and long is 0, 0. So that is used to represent this particular value. This is very, very important because normally you would see the data set in either shape file. So we have discussed that format also. So it is called .sh. So .sh is is the format of shape files, and which is used to transfer the data. So whenever we have to deliver the data in .shp, there will be another file called .proj, and that .proj file would be holding this information. So .shapefile is a proprietary data format, whereas GeoPandas, GeoPackages, all these are open source formats for transferring the your data set or a spatial data set. Now this we have discussed already above, and now whenever you have to work with the different type of data sets, it is required that you change those data set into one CRS system. Why? Because otherwise it will create wrong calculations for you. Let us suppose there are two files. One is in WSG84 and other is in a different format. Let us suppose 32,643. Which measure the distance between A to B, and one measures the distance in degrees. And if we are performing calculation onto it, and we could have a race condition, we do not know what exactly would be the right answer. So that depends upon the implementation. So it is required always that you convert all the files, whosoever you are working on a project, should be in one CRS system. So this is a very first thing. Normally the beginners do mistake that we need every file in one CRS system. So here you can see now what we have done. We converted that into EPSG 3395. So this is a number of a CRS system in which the calculations would be in meters. I hope the overall concept is clear to you guys that for each map, the CRS has to be same. So there is some practice questions which I want you to complete as you proceed and work through these worksheets. Hints are given. So if the hint is not visible to you, you can double click it and remove this detailed tag. You will start to see this. If it is not visible, I'm not sure about. So it will start to, you'll start seeing this and it will give you some hint how to do it. But for the discussion, we are going to discuss this, what we are doing here. So here, read the district data convert that into a geodata frame, look at the CRS, make a simple plot, calculate the area of the districts. Anyone can give a hint like, we have calculated the area of the district. So what would be the command for finding the area of the data set? Any thought? So why it is district dot area? Because it's an inbuilt method, first of all, and because we know that GeoPandas knows that which one is a geometry column, and based on the type of and the feature or the attribute, it will calculate that particular value. So on points, we may not be able to run the same method. So it is up to the type of the feature that is being stored here. So it will calculate like as Karanjot has suggested us. So district dot area is direct command which will give us the area of all the polygons in the geodata frame. So it is everything is happening like the pandas, and the geo series is basically, rather than panda series here, series, we call it geo series. Each column is geo series, and one operation performed on single observation would be performed on all the observations. Now, the problem here is like this way, we can also calculate district dot geometry dot area. This is one way. But the problem here is that you can see the warning that it is not in a correct CRS system. Because if your CRS system is WSG84, then the dot area would not be giving you the correct answer. So what we need to do here is we have to actually convert that into a particular different reference system where the calculations are performed in meters. Remember why you see different EPSG system, why I'm talking about multiple EPSG system. It depends upon, like, the whole earth is divided in a 2D. So there are basically zones in which it is divided. So each zone would have their own EPSG system of calculating the meters, because it depends upon where we are on this earth to calculate. So what you need to do, if you are in India, you want to use this, you want to perform the calculations on Indian map, then certainly you will be using a particular CRS system and convert all your data set into that. So you need not to bother about other EPSG systems. So whenever you will be working on Indian data, so we can share, okay, this is what is your EPSG system. Normally it is 360, if I'm not wrong, it's not in my head right now. So something like that, there is a number for it. So that number would be given to you, and then you will be able to convert your data layers into a correct EPSG system. So do not confuse it here why this is 2154. This is just a number of a CRS system in which the calculations are being performed in meters. So once it is there, we can see the data is shown similarly. but now the area is different. So if we calculate the area now, it is going to be different. Now here in this example, we try to convert this into a different EPSC number. Now it's 3857. And what is being asked is read bikes station data set. So you know how to read that data by read file function from GeoPandas. It will convert the data set into geodata frame and then convert the station data set into this EPSG system. So you know that you have to use two CRS function. Once it is converted, you have to make a plot of this projected data set and add a background map using contextually. So this we have already done in the previous chapters also. We will be using a method, a library called contextually, and then we can add an OpenStreetMap backend base map to that data set. So this whole is called map canvas. Now we are actually discussing everything which is more programmatically we can do. And just give me 1 second. Now next part is about the relationship, which is very, very important. Why I started this discussion, because spatial data is not normal data. It has some qualities and by which we can actually make faster calculations. And the most important thing is that spatial data set is related to other data sets. So there is different type of operations. Those are used for the calculations, and they are much more easier in when we handle the data spatially rather than a normal data set. So in this worksheet, you will actually work through all these spatial relations. Normally, we say that a map is a topology. So topology is, you can say, where the relationship between the objects are always maintained. So what relationship, whether it is a neighborhood, whether something is intersecting, like we say, there are two boundaries, like here, they are touching each other somewhere, or they are basically overlapping each other. If there are roads, are they, if this is a map data of roads, this is one road A, this is another road B, then they must be intersecting here, unless if it is an overbridge. So such is the relationship that has to be managed and mapped. So whether the B road is intersecting A or not. So all these topological relationships would be used for route navigation. So if we know that actually it has to be a junction here, but the point is not connected, then if we have to navigate from this point to this point, we cannot navigate via the mobile app, because it will never go from here to here, because for the navigation application, this B road is not connected to A road here. It is going overhead. So in that case, what it will navigate you is through via some other route. Now you have to go from this point to this point. Actually, you know that this is connected, but inside map, this is not connected. And due to that, your mobile application or your software is not able to navigate you through this. So such are the relationship that we need to manage. And this is one of the problem that we have to look at when we start to use the data set. And we have worked extensively on to data quality features. So topology is very important here. So we come back to some very normal relationships which are there and normally you will be using in the notebooks. One is within. So within is if you have a polygon and inside that polygon you have another polygon, so they are related to each other. The relationship is within. That one A is within B. Now, if you have two observation in a normal data, you cannot apply that easily. That let us suppose you have the data set of one student and data set of another student, you would not be able to pinpoint whether they are neighbors or not unless you have a spatial value for those two observations. So you cannot compare two observation in a normal data. This is one of the first difference between a normal data and a spatial data. Now, if we have to look at, there are different relationship within A touches B. This is also one of the relation, like whether the two polygons are sharing the same edge or not. If they are sharing, they are neighbors. So this is very easy, just one single command and we are all good. So if you want to find out, okay, find out the neighborhood of a particular multiplex. So you can run this query and you will find all the neighboring restaurants or whatever you are searching from there. Now another one is touches. So touches is, let us suppose we have to find out all the retail places or Domino's, pizza shops, which are lying onto a particular highway or road. So for that, we have to run the command that whatever is touching this B road and is a Domino's shop, that we wanted to filter it out. So touches is also one of the relationship. Another relationship is crosses, A cross B. Now, as I've told you that if both are crossing, now A is also set of, maps. So it is also set of geometry and you can basically find out whether both are crossing each other or not. And then this is for the line features. Now we could have the same feature for our one is polygon and another is a line type of feature if A is crossing B, and then we have overlaps feature. So there are a big set of relationships exist. Those we can apply onto spatial data sets. Now we move forward to look into the relationship between individual objects. So first of all, we have to extract information from the country's data set, and we can use a squeeze function. Squeeze would actually extract a single geometry from the whole data set. So this will print Belgium. Now this is Belgium. Now we have extracted from cities, like we have another data set called cities, one data set as countries. From there, we extracted Paris, then Brussels, and that has been extracted from the cities data. So 2 points data and other is polygons data. And we wanted to see whether there is any relationship between the two data sets or not. So let's visualize these objects. Before that, what we wanted to do is we want to create a line string from Paris to Brussels. And for that, we have used a Shapely file and we created and passed those points. This is similar to how we created in the previous notebook. So once that is done, now we are plotting this geo series using plot function, and you can see that there is one point which is outside the polygon, and one point is inside the polygon. Now, this is visually we actually extracted, but how to do that programmatically is to run a command within only. So there is a method, like if we have a geometry, you have a spatial feature, then you have a function called dot within. Dot within would look for whether there is something within that. So Brussels within Belgium, it is true now. And using reverse also contains, now Belgium contains Brazil. So basically this is another method of doing the same kind of thing. If we look into what about the Paris, the second point, so you can see this is false for both the cases. Now, if you have a huge data set and you wanted to look at, what are inside a particular area or region, you can apply these spatial relationships. So you can see how simple it is to apply these methods to extract the right information. Now, about the line we have drawn. So Belgium contains the line. No, it is false, but yes, it intersect with Belgium. So two spatial data sets, different geometries, but they are related to each other via spatial relationships. And we can extract the right information by using these spatial relation methods. So now we try to run that onto the GeoPandas. So you can see countries dot contain Paris. So what we are looking at is which one is having, which country includes or contains Paris. Now Paris is a point and countries is a polygon data. So wherever it is for that particular country, this would be true. And based on that, we can find out, okay, which country it is. So it is France. So only France has a point called Paris. Now, similarly, we can look at like if we have to extract river Amazon and we wanted to see which who are those countries from which this river Amazon is flowing through, and the same kind of relationship now here is crosses would be applied to get the required information. Now here is some small number of functions, those are available: equals, contains, crosses, disjoint, intersect, overlays, touches, within, and cover. Normally, earlier, when I was doing research, we were using a combination of two data sets. So one is PostgreSQL and another is PostGIS. So I don't know if any one of you is using this database duo or no, but normally PostGIS is very much mature spatial extension to PostgreSQL, which is an ORDBMS database. And this provides all these set of functions which can be applied onto spatial databases. So normally when you will be implementing something at production level, certainly you will be trying to use a much more mature system, which is PostGIS. And if we wanted to use it for routing, then PostgreSQL has an extension called PG routing that will be used to for routing and other applications. So in production environment, we usually use this combination. But as notebooks and pandas, GeoPandas are taking lead now, so there are new methods, those are being implemented here. So this is for you to practice on. Now you will try to work through it. I have told you if your hint is not visible, then please do work on it. How many of you worked on the previous, like what we discussed in lecture number, like the previous lecture? How many of you completed your tasks? Anyone? I got input from Karan Jot. Anyone else? Uh, okay, just if you are not able to do, please do complete it. I know there might be pressure onto you guys to complete your stuff, but it will be good if you can actually walk through all this stuff, because this is really good to work with, because normally in whenever you will be working, you will certainly see spatial data also in your projects. Okay, now next part is spatial join. So any question till now, guys? If you have, I would be happy to answer. I think the things are pretty much systematically placed for GeoPandas. So it is just requiring you to give effort to work through the exercises. So if you work through it, certainly it will be much more comfortable for you to understand. But holistically, I hope that you guys are able to visualize what I mean to say, how a spatial data set is different from a normal data. Is everyone clear on that this now? So if I ask you, okay, how they are different, would you be able to answer this? Any yes or no? So anyone who was there, Gayatri, Ankita, would you be able to answer what is the difference between spatial data and a normal data? Ankita, Raj, can you just unmute yourself?
Yes, sir.
Yes, please. So how do we differentiate now?
Sir, no, sir, in the spatial data, some latitudes and the longitudes are defined, while in the normal data, we do not have any such kind of location points and the coordinate points.
Uh-huh,
And in the spatial data, we are defined with the coordinate points.
uh-huh. One of the beauty of the spatial data is that it captures where, and location is the value. Why location is value? Because based on the location, everything is going to happen, as we are, developing, because location based services are on rise. So wherever you sit, let us suppose you go to Delhi, the based on the location of your mobile phone, ads would be like that way. Now, when I'm in India, I got ads onto my Google or whatever is. So those are in rupees, and whenever I'm in Canada, it changes and it just give me ads in Canadian dollars. So based on the trend of that particular life, like there are very nice projects those you can involve with. Like one of the startup that I know, they started to build like boards, like advertisement boards, and they fit that onto the car. And wherever that car moves, like we discussed about wards in the previous class. So where in which ward it goes, now it has the demographic data of that particular ward. So it knows that what type of people mostly living in that area, what is their income level, and based on that, it basically project the ad. So all such things. Not only this, you have to, your task is to find out the next location where a next retail shop should be opened. So all such would require location-based knowledge. And this is only possible because of these spatial relationship, because each observation is related to every other observation based on where they are onto that particular earth, you know. So that's the difference. So the power is where in the spatial data, which is not there in the normal data. If we take it as a normal data, we are not using spatial relationships, then that's a wastage of adding a geometry into that particular field. Mostly what happens is everyone thinks like, okay, it is just a lat long, but it is much more than that. So everyone starts with that idea, okay, this is going to be just a lat long, but exactly this is much more than that. It's where information is very, very important, because if you have one polygon and the other one is onto the next word, and you are predicting the house prices. Let us suppose we you might have done that example, the prediction house price prediction. So if you are doing it, you build a particular model. That model is trained based on the number of washrooms, number of rooms, then other thing, or the area. So there are certain parameters, but it may be possible that one locality, you all of you know, the same house in one locality A has much higher price than it may be very near house, but it is outside that locality. Now, how do we explain that thing? It will be only explained by if you know the fundamentals of spatial data science. So there is a wall in between, and these are not too related, then we have to extract it as an outlier. But normally, if we know that both are in same locality, their prices are going to be very, very high than something which is here in another locality. So I know that this is an outlier, but certainly this particular information is very, very important, because it is not only the number of washrooms or bedrooms, it is also the locality. And as of now, there is no particular regressor which you can apply where you will find the locality can be attributed correctly. So if the regressor would be attributing it or using this as a parameter, it will just be attributing this as a categorical variable. So not more than that. I hope you all now well versed with the regression system, and I hope I'm able to clearly explain what exactly this means. Now, moving to the joins, very important concept again. So GeoPandas also provide us the facility to join the data set. For that, we know that pandas provide us merge thing, and we can merge the data sets together. Now, when we are merging a normal data set, we just take care about, okay, we have a common column and we are going to create a bigger data set or table. So we merge different tables together. And but for the spatial, we can again apply the spatial relationship, those we have discussed, to basically merge different types of tables. So we will shortly see. Now I'll take an example here. The cities have been created another data frame called cities 2, where we have manually created some cities and we added the data set. We have extracted, sorry, from the cities data, and then we added another column to it, which is manually added. So now next part is from the countries. We also created another data frame, countries 2, where we have only 3 parameters. Now we know that if we have to merge something, uh, we need a common column. Without that, we may not be able to join. Is it true? Can we join without a common column or no? Any answer? Because we need a key which is used to join the two. If we just want to join without anything, it will be just Cartesian product. So it will be every row of one column and every other row of another column. It will be a huge data set, which is multiplication of all the observation from two data sets. So for this, normally we try that it has to have a common key. And you can see I'm using a function called, or method called, merge. This merge function is used to combine two different spatial datas together. Not two spatial data, one spatial data and other one is non-spatial data. So when it is combined, we see the width of the data frame has increased. Now, next part is how to handle when we have two different geometries are there. So first, let us take one data set and extract it from the main dataset country. So we have extracted France, and we look at the cities within France. So all the cities which are within France would be taken, and these are those cities. Cities are represented as points. So these are those cities which are there. Now, what happens here is we may have two different data sets which are basically spatial, and when we have to perform a spatial join, it means that transferring attributes from one layer to another layer on their spatial relationship. Now, spatial relationship we have discussed: within, intersect, difference, and there are so many spatial relationships we have discussed. Rather than on a column, we also we take the operation that has to be performed. So let us suppose these points are there and we wanted to merge them together. So merging would be done based on their spatial relationship, because a spatial attribute knows that where exactly the other attribute is. Now, if this is a polygon, now we know that it has a bounding box. We know that the point 2 and 4, when the spatial query would be executed, it knows that the point 2 and 4 is within this particular polygon. So they are lying within this particular polygon. Because we are not considering Z parameter here right now. We are just considering two parameters here. So we are not saying if this is the field, and these are some aeroplanes. We are not saying that. We are saying if this is the field, these are two trees. So planted in that particular field. So when this query would be executed, it knows that these 2 points are there. So basically the join, the key which we used in normal merging would automatically be provided by your operation or spatial relationship. I hope I'm clear on it. Am I clear on it? Anyone, yes or no? Okay, great. So for creating a spatial join, we will be using a function called sjoin, and where the cities have been passed, the countries have been passed, and now you can see what is passed here within. This is your spatial relationship. And how we want it? Left side, left join, right join, inner join, outer join. So all those join will be managed here. So all the records from the left would be taken, and if they are within that, then it will be merging together. So for the case that we have discussed above, these 2 points would be merged with the information from B polygon. So same thing is happening here. And this, you can see that joint, we have joined this whole, and then we look at the count of those values based on continent. So how many values are there for the city? So how many cities are falling within the countries? So here is Asia has 59, Africa 57. So this is kind of a statistic to us. Now, next again, the examples are given to you. You have to work through these examples. I hope that it is now clear how to apply a spatial join. The first thing you need to do is to convert both the number of data frames given to you. You have to convert them all to a same CRS system. So do not do this mistake, because this is very, very common that we normally skip to convert that into a common EPSG system. So as we now proceeding, you will see the content and the exercises are going to be little crazy and heavy. So here for this example, we wanted to map the tree density by the districts. So we calculate the tree by district, and we will be using some of the operations given by pandas. So GeoPandas is implemented on top of pandas. So all the operations which are available for pandas would be available for GeoPandas also. And then for this example, we are trying to basically map the distribution of the trees now. So this whole distribution is used to represent, okay, the data set is given, the number of trees are given, and then we divide to find out what is the density of the trees divided by the area, and then we actually map it just by number of trees per square area. So we plot the whole data, and this is the information that is in front of you. Now, visualization is very, very important when we work with maps, certainly because it gives you more, quickly you can judge it. But as we do in the plots we create in regression or other models, similarly, this is also very, very important. So you need to interpret the data set and the outcome of the plot, like what you have got. Now, another operation is overlay operation. In spatial join, we are not changing the geometries itself. So like whatever geometry is one is having, we are just keeping. Now, if we want to create a new geometry based on the relationship, then the our operation is called overlay operation. So what does it mean? Like here we have created, extracted Africa, and then we look at cities. Now, cities, we wanted to subtract the cities from the polygons of Africa. Then how we can do that? First of all, we have to buffer. If you remember buffering, buffering is padding the point to make it bigger circularly. So when we say this is a normal point, and when we pad it, it will become like bigger one, it will become a polygon. And when it is a polygon, it can be used for operations like intersecting and all that. Normally, this we do what I was discussing at the top about the road segments. Normally, what we do, we try to buffer each and every feature, and then we go on, analyzing it. So one of the quality feature that we do by buffering is, sometimes it happens that somebody has mapped a road A and mapped a road B, but this road is not connected to B, as you can see. Now, if your routing application is using this data set, then would it be possible that if you are taking your Uber from here and that is using a map where this road is not connected, would you think that this will go via this way? Do you think like this? No, that won't happen because it is not actually connected. So we run the operation. Normally, when we have a data set, we buffer, we set a limit of, let us suppose, 1 feet, that if there is another road within 1 feet of the main road, then we will snap these together. This is called snapping. So these two roads would be actually snapped together if the distance is very minute, and we call that mapping errors. And the same is happening here. What we are doing basically is we are trying to buffer the points, and would be used to those points would be used to create another geometry based on the relationship. Now, relationship is difference here. So what we did is we have one polygon, we have second polygon, and then we wanted to find out the new geometry, and that new geometry would be created by overlay method. So spatial join transfer attributes from one data frame to another based on the spatial relationship. Spatial overlay construct new geometries based on spatial operation between two data frames. So that's the difference between these two. Now you will be working through these examples, and then these examples are basically trying to portray the relationship between the data set. So normally what happens is like we have some area, the polygon, we have some another area, which is the population, and we wanted to find out the impact of something. So once we draw this polygon, we get to know, okay, this much is the area which would be coming under this. So remember, we did isochrones. So once the isochrone has been created, so we can overlay that onto the actual map. And from the actual map, we can extract all the addresses which would be, affected by something. So let us suppose we talk about the delivery. We will get all the addresses and street addresses by which that delivery boy can reach within 30 minutes. So this is also one of the operation. Now, available in QGIS, it is available in ArcGIS, very simple operations. But when you have to do programmatically, then you need to use a mechanism and you need to use the built-in methods. And that's what is kind of a focus of these lectures. We have done this all, but still I want that we will be doing in more Python-based language. So you will be implementing these in the tasks which are already given. I have given appropriate hints so that you can work on all these questions. Any question, guys, here?
Hello,
Yes, please.
sir. From where do we get these data sets?
Pardon?
So these data sets.
This one?
Yes, sir. Where we are loading geopandas.read file. So this zip file.
This one?
Yes, yes.
This is
Sir, in the
already
sec. Sir, in the
loaded.
second. Sir, in the second cell, we have loaded three files:
Yeah,
countries and
this.
populated. Yes, sir. These
So
files.
I have given you EduCollab data set. On EduCollab, I have already provided these data sets along with the notebooks.
Okay, sir. Okay.
Yeah, so from there you will download and you will work on the exercises. Please
Okay, sir.
try
Okay.
if you can download it.
Okay, sir.
Yeah. So my intent is that you work along thing, and if you can open and work along, it will be much easier for us. Now I'm about to end the GeoPandas today. So the functionality we have discussed, number one is creation of the data frames. We know the geometry is there. Then we discussed about spatial relationships, like there are relationship by which we can apply onto the data frame and then extract the information which is there. And then we also discussed about how to join different data sets together by using spatial join. It depends upon the type of two data sets. If one is non-spatial, another is spatial, you can simply merge on using pandas merging. But if you have, both are both are geometry based data sets, then you have to come up with some relationship between the two, whether it is intersecting or it is crossing or within area or touching the boundary. So all those relationship you would be using to create a joined data set. And then we discussed about overlays. Now, just we have discussed this, but quickly I will go over what plotting methods are available. One is basic plot. We know that plot function is there. If you wanted to change the size of the figure, you can pass in the attribute. And you can also color based or of column. So if you want to color something, you have to pass in the attribute to the plot function column, and here it is GDP per cap. So this is called symbology. Remember symbology, we discussed the symbology in QGIS, and using that symbology, we were able to classify our data set. So here, the symbology could be based on the column. So we can use it to classify that GDP per capita, and then we can plot this data set. So here, another example where we are using quantiles to represent the information. It's more informative now. And we can also use the GeoPandas to create and merge two different layers together. So as we were discussing and doing in QGIS, the same thing is also possible if you want to do it. The only problem here is that you cannot zoom in or zoom out. These all are static map canvases or images. So this is just a tile. We cannot zoom in, zoom out. It's not variable. So that's the difference between here, but it will give you a snapshot of what exactly you are looking at. Here it is, this code is going to create and attach three different informations. You can see the polygon data, then you see the river data, and then you have points data that is merged here. So for adding the map background, we discussed about contextually, and that would add an OpenStreetMap layer at backend. There are other packages also. There are a lot many packages actually, and some are really advanced. Some are being used by people who are working with maps. One is Geoplot, and now these are libraries. There are enormous amount of functions. Those are there. Those can be used. Each would have its own methodology, power to present the information. So another one is Cartopy, and the next one is iPyLeaflet and Folium. So Folium, I know that this is very important. Normally, people work with Folium, and this is good if you wanted to learn more. So I will say after GeoPandas, you please focus on Folium, or there is another library called Cartoframes. This is very important library given by Carto organization. They are extensively into uh, mapping, spatial data science particularly. And if you want, you can create your free account, the student free account for yourself, and that would be available for 1 year. They provide you the whole data set, the use cases. Particularly, they are into location-based services also, and they are into the mapping thing. So again, Carto is their library. Carto Frames is their library. So I'll quickly go over. This is nothing. You need not to do anything here, but I just wanted to give you okay heads up. Like this is one library that normally is coming at top right now because its visualization is really cool. So for this, if we wanted to present the, like here you can see, we are directly reading from the cloud. So read Carto, the name of the data set is given. So this is a points data set, and it is represented like this. A really cool observation data set and presentation. So it depends like what visualization you wanted to give. So one thing is like a real data is there. This is a polygon data, and you can present this as now this is more interactive thing. So interactive information is there. Legend is also available, and you can use this library for visualization of different data set. Now the lines data you can see really cool. Basically, symbology is very cool. How the turns are represented, how this whole information is being represented is called the style sheet of their map. So they are using very nice, smooth style sheets to present the information. Now, points pattern, and you can also publish your stuff onto, you need just a Carto account, and for the students it's all free. So I hope this give you some more insight into how to use GeoPandas, and further we will do dive into next concept of the spatial analysis, spatial data science. We have discussed about uh, thinking, we discussed about computational environment, we discussed about spatial data, and now is very important topic, spatial weights. This will be used a lot for spatial data science because we know that each and everything is related. Today we discussed about that what distinguishes between normal data and the spatial data. So we agreed that the where and how the observations are connected is very, very important. So when we talk about the observations are connected, certainly there might be some links, and we have to calculate those links and to make some predictions about the patterns. Normally, if we have a disease somewhere, we have to identify its distribution pattern, how that would spread, what would be the pattern, what would be the hotspot. It depends upon the type of application. Let us suppose you are working on lines data, you have to work on graph theory concepts, like where are the all the points which are very, very, very far from it. And I remember in the previous lecture we were discussing about finding the choking points in a road network. So those choking points would be the one where most of the time people are moving. Like if we say that we have the road network. This is more planned road network. So now this is a road network. Now you need to identify the choking points. So you know what is your job is to convert this into a graph, and from the graph you will try to give some weight to each and every junction. So initially you will try that. Now these are roads. The people would be starting from different points around these roads. So what is your job is to put those dummy points onto the roads at some distance. And from each point, you try to create a route that goes to every other point in the data set. Now, suppose if this is the condition, how compute intensive this calculation would be. Like if we have to calculate, like in this one segment, we have 10 points, and from each of these points, we have to calculate all other points. This is going to be very, very compute intensive. And also what we will do is once we have all these routes, we will find those vertex, which are highly used. So it may be possible if this is broken, you can see that every traffic would be happening through these two junctions. And this is already happening. So if somebody has to go like this, if somebody has to go like this, everything is happening through these three junctions. And this kind of calculation is very, very important for urban planning. And one of the most core area where this whole spatial data science focuses on is urban planning. Now people are using it for different applications, but urban planning is very, very important topic. So I just wanted to know about your, like, can you listen more, or we should stop or talk in next lecture? I just want to ask you. I wanted to complete this spatial weights, but it is very long discussion again. It will take around 30 to 40 minutes. If you agree or you wanted to stop today. Any any ideas, guys?
So we can continue.
Continue.
Yes, sir. From my side, if other agrees.
Yeah, if you can just yeah, you are a latecomer, Ravi, I think.
Yes, sir.
Yeah. So, what others say? Do you have time to discuss or no? Can I move? One yes or no, whosoever is. The Karanjot is one who was there earliest one. So how about you, Karanjot? Because there's a lot of stuff that you guys need to complete on those notebooks. So I would suggest that you go through that material. So my say would be that. But I still would go quickly over what are spatial weights. So spatial weights, again, as I was talking to you, that whenever there are different blocks or features coming together, we need to apply certain methods by which we can identify their neighborhood. So one of the thing that spatial weights are calculating here is the weightage to the neighborhood. So how that is calculated uh, is basically using weights. So those are called spatial weights, and different names are used, different methods are used. Why weights are very, very important? Because it is Tobler's first law of GAS that everything close is more related to everything than everything residing away from that particular point. So close things are more closely related to each other, and those would have same attribute. This is a general law of geography, and these weights are trying to capture that, because if we are able to capture that information, like which observation are closely related to each other than others, then we try to find out. I know we apply clustering as an EDA step for normal data, but here we talk about where the location, and location is dominating than all other features. Like if you have a small house in a very good locality, even then its price would be very, very high as compared to a normal house somewhere else. So locality is the power, and these weights are trying to capture it. Now, the first one is contiguity weights. So in this, I'll share with you this notebook, or you can download it directly from this GitHub page and try to work through this. What it is going to show here is, let us suppose we have nine polygons. So contiguity says to our neighborhood if they have a common edge. So 0 would have like its neighbor is 0, 1, and its neighbor is 0, 3. So neighbor of 0 point is 1 and 3. This is captured here. So this dictionary is explaining it. So 0 has 1 and 3 as its neighbor, 1 has 0, 2, 4 as its neighbor, so all this is used, and we can say these are called adjacency lists. Adjacency list, if you remember, you might have done that in data structures. So adjacency lists are used to look at which one is the adjacent of a particular node. So the same principle is used in this. And now this square is representing the relationship that P0 is related to P1 and P3, P3 is related to P6, P7, P4, P1 is related to P0, P2, and P4. So this is how this is a representation of the relationship, and this is represented and called Rook neighbors. This is the term that is being used, Rook neighbors. And for that, the method is available, which will find out once you have the data set, the spatial data set, it will find out the Rook neighbor from there. So let me show you. I think I missed it above. Yeah, so here it is. So here it found the Rook neighbors from a given data frame GDF. So we give the GDF and it will find out the neighbors. Why it find out? Because we need to know who are neighbors of that particular polygon. We are talking about polygon. We are not talking about lines data. We are not talking about points data. We are talking about polygons data. Okay. Now another method is says, oh, we can consider two as a neighbors if they share a common vertex vertex. So by this method, now you can see that P0 is also neighbor 2.04 P04 because they share a common node. Now this method of identifying the neighborhood by using a common node is called queen. This is called Queen's neighborhood. So it will try to find out those relationships. Now you can see here the neighborhood has increased. 0 polygon is actually neighborhood of 1, 3, 4. 1 is neighborhood of 0, 2, 3, 4, 5. I hope you got it now. Correct? Are we together, guys? Okay, thank you. So again, there is contiguity.queens method, and which will find out the neighborhood based on the concept of common node. And then we have contiguity.rook, which will find out the neighbors based on a shared edge. So that's the difference. And based on that, weights are assigned. 1 is assigned if there is neighborhood. 0 is assigned if there is no neighborhood. To create a sparse matrix, zeros are always removed, and just ones are taken. So this is the dictionary of weights that is there. Now, if somebody says, I want to find out, predict the house price, you will see, okay, what are the nearest localities? What is the value in those localities, and what is the value in within that particular locality? So that would add a value to it. If you know the neighborhood, you can predict better. Google is coming into real estate. They are going to ask the neighborhood, what is the price of your neighborhood plot or house? And based on that, if somebody is going to sell a particular house, they're going to announce that this is what would be the predicted value of that house. So all this would be captured via these relationships, and these are very, very important as we proceed through other concepts which we are going to focus, particularly auto correlation, spatial correlation, regression, and other stuff. So these weights are very, very important, and even these are important when we will be working on a network type of geographical data set. Now, cardinalities, you know how many relationships are there. So for 0, it is 3, for 1, it is 5, and we can present that information in the form of histograms here. So you can look at like what are the neighborhoods of each particular polygon in that particular given data set. Now, when we have spatial weights from a real life data set, it's normally, as we were discussing, shapefiles are non-topological. They do not save the relationship between the objects. We have to extract it. Okay, so normally for topology to be added, either we have to extract or additional file has to be supplied. So this is trying to load some data set, and then we try to create the weight vector, weight matrix, which is now Queen's method. Now, if it is Queen, then it means that it will try to find out the common node, and based on that, it created the whole. You can see that how complex this neighborhood chart is, but it tried to find out the neighborhood to each point. So this is a zoomed version, and you can see that here, this is the histogram, which shows that like around 6 to 7, there are basically number, which is having like this 6 to 7 is normally each polygon have 6 to 7 neighbors. So those are being represented by high rise tower here in the histogram, and then there are some outliers also. So there is an outlier which have more than 15 neighbors, and there are some which is having only one neighbor. So those are kind of situation which is presented here. So if we go by Rook, then the number is quite low because we just ask for the shared edges. Now, there are distance-based weights also. When we talk about distance-based weights, so in that, K nearest neighbor weights are also applied. Like, we don't know how many we should actually consider as a neighbor. So as again in KNN algorithm, and the K is always an optimization hyperparameter. So here again, coming back to this particular problem, we say how many we should consider, like how many nearest neighbors we should consider to predict our model. We can see that there are more than 15 neighborhoods for a particular polygon. Then we can say, okay, there is one method which set the value of K and see the impact, and then optimize the value of K to find out a better model. So it is set by user. So with K is equal to 4, we can see the weights are, different. But the only problem is with KNN that for each of the polygon, it will find out that there are 4 observation or 4 neighbors. So that is one thing which is problematic. So other than that, there is a kernel weight. Now kernel weight tries to apply Tobler's rule, and this Tobler's rule, I will just go over the diagram that would be easier to grasp. Now, as per Tobler's rule, kernel applies a decay factor. Like if a polygon is away from a point which we wanted to calculate on. So let us suppose if we are here. So if we are here and we try to find out the relationship between all, so it will try to decay. There is a decay factor. More the distance, less is the impact. Okay, so that is used in kernel calculation, and this is a kernel centered on first track. So here is the first track, and then as we are proceeding and going away from it, you can see the impact is changing. The weight is changing basically. So if we are here, you can see here, this whole area is very close and neighbor to it, and all other area is away from it. So the weight is same here, and weight is changing to the farther polygons. Okay, so this way kernel methods are very good for the application. You got the point or no? Did you get the point? Like what we exactly doing is we are applying some methods by which we'll try to find out the neighborhood. We're trying to give the weight to the neighborhood. And for that we use different methods. And one of the method is kernel method. It applies a decay factor onto the distance. Farther the polygon, higher is the decay factor, less is the weight of neighborhood. So that is applied by kernel method. Then there are basically hybrid mechanisms also, not only the distance, but we can combine our different methods together. So weights, as well as we can say distance and kernel method is combined together to create a better mapping of the weights or neighborhood. So this all chapter is focused on to calculating the weights only. So another part is great circle distances. Now we discussed the distance, whether to take Euclidean distance or to take, now one Euclidean distance, okay. So if there are points A and B, we can find out the Euclidean distance. But if the points are on Earth, now Earth's surface is elliptical, so it is not going to be straight line. It is going to be something like this. Okay, so sorry for, so it's going to be like this. So distance would be different, basically. If we have to calculate that distance over Earth from very farther point, then direct line distance would be very far from the actual distance because there is a curvature there. So normally what happens is that the great circle distances are calculated, and for calculating these great circle, there is a method called Haver-Sein method that is used rather than Euclidean distances. Okay, so if you have to find out the distances between the 2 points. Now, these are the operations which are explained if you have a disconnected observation, then how to handle that particular observation. And last one is block weights. These block weights are basically the polygons are created as in a block, and the same is same weight is assigned to that, and it is attached with other method. Now here two methods are combined together. One is queen contiguity weight, another is block weight. So what is done here, you can see this is your first level where we are trying that we have continents. So there are different continents and their queen connections. So queen connection have been made. Now you might be astonished why this point is taken, why not many points are taken. So because in polygons, whenever we process, we take the centroid of the polygon as a point to represent. So whenever we say, okay, when we say Ludhiana on a map, there we see a very one point which is representing Ludhiana. And when we keep on, going down or zooming into the map, then we start to see a different point. Normally, each and every map polygon would be represented by its centroid. So here, all the centroids are calculated automatically for each and every polygon. So that's a mathematical operation to find out centroid of a polygon. And once it is done, all these points are giving the queen distances and create the matrix. And within that is a block method. Here is, you can see the block is created. The block would be used based on some method. What would be, so here you can see there are 4 or 5 blocks. Those are created for all the continent, and then they are combined together. So within the blocks, another computation of queens have been performed. So within that block is happening, and you can see the difference between the vectors. So here it's more spread. This is complex, and this is the most complex kind of weight vector calculation. I know that this is overwhelming, but what is the takeaway from this is that we have to calculate the weight vectors of neighborhood, and for that we have different methods, and we can use certain hybrid methods to calculate the weight of neighborhood for each and every given type of data. It is up to us which to apply. So given there are different are given, and then they are joined together. So that's what this whole chapter is trying to answer. So what I need from you guys is, how many of you are there? Like 5 people. So if you can work on these, and each one of you can do first 5 questions, that will be really great. So I will assign it to you. Okay, so question number 5, Karanjot. 4, Ravi. Number 4, Ravi. And then you have question number 3, Braj is there. Puneet. Puneet, would you be able to do it? Puneet, are you there?
Yes, sir, sure.
And then Ankita, second question. And then Gayatri will be doing first question. Okay. So Braj, for you, I think you can take one of the questions. All of you agree on this? Will you be able to do it? Just send it over to me as a one combined file, or just send me via email. So my email, that you can send it to me. I'll merge it together, and then we can, I think we will be good. There are certain questions that I wanted to ask you guys. Let me stop